Uh, so today we're happy to have Semon Rezchikov currently at the Institute in Princeton, and he will speak about categorical aspects of the Fueter equation. So please.
All right, thank you so much. Thank you for giving me a chance to speak at the M seminar. So let's just get to it. In this talk, I will talk about this proposal, which different people have thought about at different times, to assign some kind of two-category to a hyperkahler manifold when you have a background distinguished complex structure. And this particular talk is based on kind of my own thinking about this sort of set of ideas that was done in collaboration with Aleksander Doan, who's now at, I think, Imperial, but we did it when he was a postdoc at Columbia. And I've also benefited a lot from talking with Justin Hilburn and Benjamin Gamage about the sort of ambient kind of connections of this story. And from kind of this, one way to think about all this is that, symplectic topology and the Fukaya-Category and all these symplectic invariants are based on analogies to real Morse theory. So, complex symplectic geometry, or whatever that should be based on analogies to complex Morse theory, which is a very old idea. Maybe you could say it goes back to Picard and Picard-Lefschetz theory, but there are sort of different parts of it, which were kind of explored by different people for different reasons. I'll mention some of their names as we go through the talk. And surprisingly, kind of that whole perspective, like what is complex Morse theory, sort of finite dimensional model, has never really been fully kind of cleaned up and developed, although there's been some progress on that recently, which is exciting. But the basic heuristic that one can keep in mind is that when you try to complexify various invariants, you often categorify those invariants. And the reason for that is basically because, the real numbers are one-dimensional and the complex numbers are two-dimensional. So a higher dimensional TQ of T leads to categorification. And so we'll try to take a sort of Floer theoretic approach to the whole story rather than some sort of algebraic approach. And from that, we'll find that there are some interesting sort of phenomena in partial differential equations. And thinking about these kinds of PDE questions from this perspective, sort of interplay between categorical ideas and sort of questions and analysis has been at least enlightening to me and like help find some things that one otherwise wouldn't try without that perspective. And there's lots of puzzles here. Some of these are kind of more algebra and physics puzzles, which I don't understand, and I'll try to mention them. And my personal hope is that, thinking about this from this sort of like boundary between differential geometry and algebra perspective will help kind of both sides, people who study these sorts of 3D n equals 4 and 4D n equals 2 theories. And I'll mention how those arise in the story. Okay. So that's the sort of, those are the general goals for me. So let's just get to it. So I said we're supposed to complexify everything. So let's think about the basic finite dimensional model. Well, real Morse theory assigns to a Riemannian manifold and a real Morse function a vector space. And the vector space is built out of the critical points of the function, as well as real gradient trajectories, which are solutions to this kind of real gradient flow equation. Those are used to define the differential on the Morse complex. So, d of x minus is x plus. And already here, there's a choice, like do you use the gradient flow of f and the gradient flow of or minus f? So that choice, those two groups are kind of not naturally isomorphic, they're dual to one another. That's the sort of flipping the Morse function to minus itself as Poincare duality. And there's something similar that happens in the kind of complex setting. So in complex Morse theory, we try to complexify every word in the previous sentence. So complex Morse theory assigns to, a complex version of a Riemannian manifold is a Kähler manifold, and a complex version of a real Morse function is a holomorphic Morse function. And instead of a vector space, we assign to it a category. The category should be built. Well, the first approximation to this whole sentence should be that it should be built out of critical points of the complex Morse function. Those should be the objects. The morphisms should somehow be counts of real gradient trajectories between these complex critical points. So there's a complex valued function, so it's not clear what a real gradient trajectory should be, but you can just take the real part of the function or any one of its rotations by phase. And then the morphisms, so those are the objects in the morphisms, and then we need some composition on the morphisms. Those should be given by counts of complex gradient trajectories. So that's this equation down there. So one way to think about this is, well, we replaced the real line by the complex line. We replaced differentiation in the real coordinate by like d bar in the complex coordinate. And then on the right-hand side, we need to still put a vector field. So you can say the gradient of the real part of f, but really you could have just said, we take the differential of f and then we use the Hermitian metric to dualize it to a vector field. So this you can write this in a more even more way analogous to the real gradient flow equation. And this is the idea that there should be some category associated to this kind of complex Morse function is an old idea, and a lot of people have worked on different parts of it. Some aspects of this were sort of explored in Donaldson Thomas's paper on higher dimensional gauge theory. And then this is kind of the algebra, kind of some various proposed algebraic perspectives, from physics motivations, were done in a work of Gayotomor-Witten on the algebra of supersymmetric field theories. And then there was sort of a kind of a mathematical perspective on that work done by Kuntsevich-Soibelman in this paper on algebra of the infrared. And then separately, there's something that
actually you missed Kapranov, who was.
Yes, I'm so sorry. I think he was also there. I'm sorry, I should have put that there. Thank you.
And moreover, we categorified that paper with Kuntsevich-Soibelman and Kapranov. We had a paper with Lev Sukhanov, like Kapranov, Soibelman, and Sukhanov, where we categorified. And so it's actually categorification of the algebra of infrared. So since you are talking about categorification, maybe it's a good place to mention it.
Okay, yeah, I'm not familiar with that paper. Thank you. Yeah, and then, so separately from some of these kind of works by following kind of Gayotomor-Witten's proposal, there's a proposal of Hadish, and that, which was motivated by complex Chern-Simons theory, essentially. And that proposal was recently kind of various analytic details in it were sorted out by a sort of a long paper of Dong-Ha Wang. I'll mention something about why the Hadish proposal is easier to kind of analytically, and I'll say something about the kind of open analytic problems in these other proposals. Okay. So the basic thing one should notice about this complex gradient equation is that it has a symmetry. So the gradient of the imaginary part of a function is that I times the gradient of the real part of a holomorphic function. That's just the Cauchy-Riemann equation. And so this equation, you can write it. One thing that means is that if you rotate the domain, that's the same equation as multiplying the set of solutions to this equation with a rotated domain is the same as the set of solutions to this equation where you multiply f by e to the I theta. And of course, you can also translate in the s direction, so in this solution to this equation. So this is a sort of equation with a C star, with a C with like rotational and translational symmetry. And that's important for the analysis. It really makes it quite different from something like the Floer equation. But this is, a Floer equation on a plane. So because of this fact, this is really just these gradient flows. These real gradient flows of f or its rotations are the same as flows of I times the gradient of a rotation of f. And so that means that they're actually Hamiltonian chords between these critical points. And so this equation is actually just Floer's equation, which has, you would think it has a pretty well-developed analytic theory. And so the morphisms of this sort of spaces of solutions, this complex. So the idea is you have some space of, so if you have two real gradient trajectories, then you can look at the space of complex gradient trajectories which sort of flow from one to the other. So, if you set ds equals 0 in this above equation, you can write that above thing as a real gradient trajectory. And so you can ask for, in the s minus infinity, s plus infinity limits to sort of asymptote to real gradient trajectories. And then this is just some kind of like Floer complex for some Hamiltonian action functional, essentially. So it sort of seems like an object of Fukaya category theory. But it's very different because this domain C is very different from the sort of usual domain in Floer theory, which is a strip. And similarly, these Hamiltonian chords on R are very different from Hamiltonian chords on, or maybe you could call them Hamiltonian heteroclinic trajectories. Those are very different from Hamiltonian chords. But that's the basic observation, kind of an interpretation. You can notice that this is some object that should arise in Fukaya categories. That's one thing to say. And the other thing to say that's related to the symmetry of this gradient flow, complex gradient flow equation is that this category actually depends on a background angle. So you can think of this choice as background angle as analogous to the choice of positive or negative gradient flow in real Morse theory. And there's actually some duality between sort of the category defined at the background angle theta hat and the background angle theta hat or theta bar and minus theta bar. That becomes some causal duality between those categories. And if you fix the kind of way to think about this is that this complex Morse category should be some category defined in terms of symplectic geometry, but done in an alternative model that never uses sort of traditional symplectic objects. So a critical point should correspond to a Lefschetz symbol coming out of that critical point. And
so let me, you started with a so big speed that I'm kind of far behind. So you will consider only Morse functions f capital. Huh? No?
For now. I will then say something about, I will at some point need to use a Morse bot function f. And I will say
but
what I don't understand in general.
If I drop Morse completely, no Morse bot, no Morse Smail, nothing. Sure. So in the end, will you have any proposal for that? Because in real life, they almost never Morse or Morse bot.
I will not have a general proposal for that. And I believe that there's plenty of interesting subtleties in trying to define that notion.
Yeah, I mean that since you kind of probably will concentrate on some analytic issues, so algebra geometrically, there is a very easy way to handle arbitrary complex, say, algebraic function, taking the sheaf of vanishing cycles.
Yes.
And so, but the point is that
I will already mention something about that. At
least there is no known to me analytic approach to this definition. So I do not know what analytically or differential geometrically means to define the sheaf of vanishing cycles. So you don't have gradient trajectories; it's completely different world. So I'm just kind of I do not see. I would like to understand the level of generality in which your proposal will work. Yeah,
so I will describe something that works in. So I will state some precise theorems, and they will be in some Morse setting. Then I will discuss what are the issues that one needs to solve when generalizing from the Morse setting. I'm happy to talk about what I know about partial resolutions to some of these issues.
All right, okay. Yeah, I understand. So then,
for example, with the sheaf of vanishing cycles, there is an interesting already difference that you could choose. If you have which is somehow important, I think, in this story, which is that if you have a holomorphic function, then on a non-compact manifold, it's not obvious how to treat the sort of geometry of the holomorphic function at infinity. So even if you have a compact critical locus, so then this
yeah, in finite dimensional case, it's not a problem. In infinite dimensions, which maybe you have in mind, yeah, but in infinite dimensions, I even don't know what we are talking about. In finite dimensions, we proved some theorems with Maxim and some other people, maybe, about nice compactifications, which seems to be correct. So, I mean that algebraic geometry, it's sort of an easier topic in some respect than analysis, so you don't have to prove some estimates. Yeah. All right. Go ahead.
Great. Yeah. So this is the sort of formal proposal, which can be made rigorous. I mean, I will say I will try to be clear about what's been done, and I will say something about what I think are the different pieces of trying to generalize it to a kind of more general setting. So if you choose a background angle and you have a Morse function, then that should correspond to a Lefschetz thimble coming out of that critical point, and that the direction of the Lefschetz thimble, its projection under the function itself, should be a line in the direction minus theta bar. So that's why you need to choose this direction, because these different Lefschetz thimbles for different angles really can be quite different. They're like, don't even have to be homologically equivalent in any sense. Now, the morphisms should, well, they're supposed to be built out of gradient flows between these functions. Well, in the simplest settings, and I'll draw a picture in a little bit, these gradient flows are in bijection, or at least are kind of cobordant to the number of intersections between these Lefschetz thimbles. If you make sense of this intersection number by pulling one forward. And so then, while these complex gradient flows, there's some kind of solutions to Floer's equation on a plane. Those kind of look like solutions to Floer's equation on a strip. And you see that, you know, the objects on the left-hand side are in kind of loose bijection with objects on the right-hand side, which are the things that you use to define the symplectic invariant called the Fukaya-Seidel category of a symplectic Lefschetz vibration defined by this complex Morse function. And so that's the sort of model which people use to try to make sense of this complex Morse theory story. At least that's one way of so this category, whatever it is, in sort of finite dimensional cases, when this complex Morse function has some nice behavior at infinity, should give you the Fukaya-Seidel category of that function. Okay. So these background angle is kind of important. I'll say something about how we use it later. So, you know, there are these categories for different choices of background angle. They have non-trivial isomorphisms between them. In particular, they don't send like a Lefschetz thimble at the critical point P to the same Lefschetz thimble at the critical point. They send it to some kind of complex of those Lefschetz thimbles. And in fact, the whole monodromy around the sort of family of angles is a non-trivial functor. It's called the Serre functor of this category. So that's something. So the category doesn't depend on the angle, but in a pretty non-trivial way. Okay. So here's the sort of picture of what I was saying. You know, if you have two critical points, you can pull out these Lefschetz thimbles. This is the picture up top. And then if you try to move this bottom Lefschetz thimble up, then you would have some number of intersection points between those Lefschetz thimbles. But then, you know, these Lefschetz thimbles are just ascending or descending manifolds of a real gradient flow. So these intersection points are in bijection with broken real Morse trajectories. So you flow at one angle, and then you stop and you flow at a different angle. And then you can kind of deform that equation. And then you would kind of, you know, you would get some cobordism of moduli spaces. So you would say that the number of intersection points is the same as the number of direct gradient flow lines between these critical points. That's one sort of motivation for why there should be some relationship to some symplectic category. And then the thing I just wanted to say is, like, how would you use this complex gradient flow equation to build some composition on morphisms? So if we have some three critical points, which are kind of on the bottom right, when we have three gradient flow lines, which are these gammas, then you would try to solve for this complex gradient flow equation on the plane. And then on each, you would divide the plane into three pieces, and then asymptotically, well, you can do some change of coordinates. You like take like basically power of z to make this fraction of a plane into some half plane. And then you would say that asymptotically in those coordinates in that half plane, the solution to this complex gradient equation limits the corresponding solution to the real gradient flow equation. Okay, so that's how you would at least hope to define this kind of category. So that's the sort of the basic intuition. I'll say a couple things about what goes wrong with that and what can be done to fix that. Okay, but this is the basic intuition.
But it's sort of a very, very old idea.
Yes, this is a very old idea.
Yeah,
and it has never been made rigorous. Okay, so I mentioned that these Lagrangian, this kind of the angle is really important. So if you try to move this bottom blue guy on the left through the sort of angle connecting this bottom critical point, this middle critical point, then the homology class of these things change. And so, you know, the number of direct gradient flow lines wouldn't really be in bijection with the in any sense with the number of intersection points between these kind of Lefschetz thimbles going to the right. And so that suggests that, maybe sometimes you can pick a base point somewhere. So you like look at broken gradient flows, and those are in bijection with sort of not the obvious Lefschetz symbols by some non-obvious ones. But that's the sort of Picard-Lefschetz phenomenon, and that that leads to like at least there's one way of modifying this sort of direct straight line setup to improve the situation analytically. Okay, so the other thing to say is that when you apply Hochschild homology to the sort of complex flow category, then you get this complex Morse category, then you actually just get the direct sum on these critical points. So you get some kind of real Morse group, basically, of the real part of this function. And which real function? Well, it's the one corresponding to the background angle. And that's important. And then the point is the Lefschetz symbol naturally lies in this relative homology group. That's this map. This can be understood in a couple of different ways in terms of open closed maps and so forth. And then there are these non-trivial isomorphisms on these categories. If you change the background angle, so that gives you isomorphisms of these homology groups, and the maps on those are just these Picard-Lefschetz transformations. So if you have these symbols, then they change as you move around. And you should think of these Picard-Lefschetz transformations as these Stokes data for this oscillatory integral. And again, Semon and Soglin have written a lot about this kind of idea. Although obviously, sort of basic idea has a lot of history, Lagrange and so from Stokes, I guess. One thing I want to say is that if there's this sheaf of vanishing cycles, and my understanding, it doesn't have to be the same as this group in general, because they sort of the Morse function kind of have critical points at infinity, and that's I guess related to this work on compactifications. I don't really know all that much about that. Okay, so there's a bunch of reasons why this is challenging to make rigorous. The first reason is because the complex gradient equation has this extra symmetry, the compactification of the space of complex gradient trajectories, kind of done in the way that I wrote down, is pretty different from some kind of A-infinity compactification. There's a conjecture about this compactification that's in Gautam-Moore-Witten, and then it's sort of reformulated in some other way, Kapranik and Savage and Soglin. There's still an open problem to like really show that these compactifications are correct. Another challenge that's related to this previous challenge, that there's no energy identity, at least naively, because if you think of this as some Floer equation, well, the energy of a Hamiltonian map on R is infinity. So like whatever the energy of this plane is, it's like a difference between infinite numbers. And so you have to, in one way or another, renormalize the energy to actually extract some quantity over which you can control like the geometric energy, so the L2 norm of the derivative of this complex gradient trajectory, which is what you need to understand its limiting behavior. And then there's kind of lots of other more technical problems, like the Fredholm theory of these kind of non-compact domains is pretty subtle. So one thing that was done is independently of this Gautam-Moore-Witten proposal, Hadish proposed a different version where instead of using straight line flows, you use these kind of curved flows. And then these curved flows are not kind of automatically in bijection. The numbers of these curved real gradient flows are naturally in bijection with the intersection numbers between these symbols. That's kind of like the picture on the left around the picture on the right. And then the compactification becomes more like a normal A-infinity compactification rather than some modified compactification proposed by Gautam-Moore-Witten and others. And so that was, the situation as of like the beginning of last year was that, okay, we had these two proposals, that kind of interesting. But then Dong-Ho Long wrote this very long paper motivated by kind of problems in Seiberg-Witten theory, which basically made the sort of analysis of the Hadish kind of thing rigorous. So, he kind of solves this kind of renormalization problem and shows that the compactification, when you have these curved gradient trajectories, is actually the usual A-infinity compactification. Okay, so there's at least some model now of this complex Morse category. Although, it's still interesting to try to make sense of the other model with these straight line gradient trajectories, in part because it might be easier to compute in. It's hard to count the number of curved gradient trajectories when you kind of pass to some infinite dimensional functional, which we'll do next. It's also interesting to think about the geometry and infinity of these functions. So that corresponds to basically like when can you get compactness for these solution spaces. And also very often when we start studying these functions, they're not going to be Morse. The critical locus doesn't obviously have to be compact. And there's just a lot of different interesting problems there. I personally, at least, understand what you would do if this function is Morse bought. And that's already like kind of, I mean, maybe it's sort of natural, but at least I haven't seen it written anywhere. And it's already kind of a little bit subtle. But if it's more spot, you should somehow glue together the Fukaya-Categories of the different critical loci by these sorts of using these real gradient trajectories going between different critical loci. And when the critical locus is non-compact, then it's like really quite non-obvious what you should do. And that's kind of related to this problem of like, what if you have if you're dealing with some kind of Morse theory in a non-compact space, you have to understand how to treat infinity. So you might have to perturb your function in some way. That can bring in new critical points because basically you could have some function whose like derivative goes to 0 at infinity in some direction. So that's an interesting challenge for making sense of these constructions at greater generality. Okay. So anyway, let's go on. So this is now try to think about complexifying symplectic geometry. If you have a symplectic manifold, then, what we usually do is, we give it a metric by picking a compatible almost complex structure J. We assign to the symplectic manifold the Fukaya category. So I've mentioned this before a couple of times, but this is some category which has objects, Lagrangians of manifolds, morphisms, the Morse theories of these symplectic action functionals, which are these things written in the middle. So these are some function on the space of paths between the two Lagrangians. And there's this optional thing you can do where you can add in an extra term, this Hamiltonian term, which is interesting. If the Hamiltonian term is small, it doesn't matter. But if the Hamiltonian term is large, especially large at infinity, that it actually changes the Morse homology group of this Morse function. So the Morse homology group of this Morse function is called the Lagrangian Floer homology group. And its gradient flow, it counts these holomorphic curves, possibly with this sort of interesting perturbation on the bottom. And that's sort of the beginning of a lot of stories about symplectic geometry, because now that you have these holomorphic curves, you have 3 Lagrangians, you can compose between them using solutions to the same kind of equation. But now instead of having 2 Lagrangian boundary components as above, you have more Lagrangian boundary components. Okay, so that's the sort of standard story. So I'll say something about the complexification of this story, and then at some point I will say some results, and then I'll generally talk about kind of some ansatz for when you can try to guess this category, and maybe some questions I'd like answered. So how do you complexify symplectic geometry? Well, it's an interesting question. There's kind of an obvious answer, which is the one we'll start for now, which is that you have a complex manifold with an I-holomorphic symplectic form. Then the problem is if you want to build some invariant of that, you usually have to pick some kind of metric. And so the natural kind of strong metric version of a complex symplectic manifold is a hyperkahler manifold. So now you have like 3 complex structures. You have an action of the quaternions, which is covariantly constant with respect to the Riemannian metric. And then that automatically gives you 3 closed symplectic forms. And then if you choose one of the complex structures as distinguished, which we will always do, then there's a corresponding holomorphic symplectic form coming out of the combination of the 2 other real symplectic forms. And then you should, really there's a whole twister sphere of complex structures. In the hyperkahler case, they'll all be integrable. And because we're thinking of one of the complex structures I is distinguished, then there's a kind of, that's the north pole on the twister sphere. There's a corresponding equator. And the symplectic forms that are compatible with the complex structures on the equator are the real parts of this holomorphic symplectic form. So that's something to keep in mind, some basic structure. And then we can ask what's the, so before we had like real Lagrangians, so now we should clearly have complex Lagrangians. These are I-holomorphic submanifolds, which the complex symplectic form restricts to 0. These are real Lagrangians for a whole circle of symplectic forms, the equatorial symplectic forms. And now, so what do we want to do? Well, we want to complexify that symplectic action functional. Well, there's a natural, you can write the same formula. It's the differential, it's some functional whose at least differential should be the integral of this 2 form over this path. So it's a 1 form on the space of paths, and it's a holomorphic 1 form, which if this complex 2 form is a primitive, which happens in many cases, then it's just the integral of like this primitive lambda over the path. That's a holomorphic function. And then this function will be Morse on this path space if the Lagrangians are transverse. And it'll its real parts will just be all the real symplectic action functionals with respect to all these equatorial symplectic forms. Okay, so that's the sort of picture. And then what you want, so what did we do? We complexified the symplectic manifold, we complexified the Lagrangians, we complexified the symplectic action functional, and now we want to clearly use complex Morse theory to define the morphisms. So you should say that, you know, there should be a morphism category between two complex Lagrangians. That should be morally the Fukaya-Seidel category, this complex action functional. And then, because of this Hochschild homology observation about real Morse theory, if you take the Hochschild homology of this hom-category between two complex Lagrangians, then you should get the usual Floer homology of these two Lagrangians, thought of as real Lagrangians with respect to one of the equatorial symplectic forms. And the background angle is important because the choice of background angle tells you which symplectic form you're thinking about. So that's important. These Lagrangian Floer homology groups, these different choices of real symplectic form, I mean, they're all going to have the same dimension, but their isomorphisms between them are non-trivial. That's something that I'll mention later. Okay, so that's the basic picture. So, you know, what are the objects supposed to be here? So of this hom between two holomorphic Lagrangians, it should be this complex Morse theory of this complex symplectic action functional. So its objects should be critical points of this complex symplectic action functional, which were the intersection points. The morphisms should be the real gradient flows of this complex symplectic action functional, which are just real gradient flows of real symplectic action functional. So we know what those are. Those are just J Theta holomorphic strips, where the J Theta are these equatorial structures, complex structures. And then the differential in the composition should be given by complex gradient flows of this complex action functional. And you go compute and you get an equation that looks like this. And so this equation, or its modifications, is called the Fueter equation. Okay, so it's this sort of, you have like some manifold with a frame, and then you basically say that the quaternion linear combinations of the derivatives of the map with respect to the directions given by the frame, their sum is 0. Okay, so that's a Fueter map. Okay, so the complex gradient trajectories of the complex symplectic action functional are these Fueter maps. Okay, so one thing I want to say is like a different way of thinking about where this equation comes from. What you want to ask for is if like when is a map from the quaternions to the quaternion kind of, well, you can ask for it to be the quaternion linear, or you can try to ask for it to be quaternion antilinear, by which I mean like the space of linear maps from R4 to R4 or R4 to R4n is, you can decompose it in the quaternion linear maps, or it's perpendicular. And this is the condition that it lives in, it's perpendicular. So you can think of this as a generalization of like the anti-holomorphic curve equation. Well, this kind of generalization where you ask for this map to be quaternion linear it actually behaves very differently. You sort of lose the symmetry between anti-holomorphicity and holomorphicity in higher dimensions. So Fueter basically pointed out like 100 years ago that if you ask for a nonlinear map whose derivative is quaternion linear, then the whole map will actually be linear. So there's but there's lots of interesting kind of quaternion antilinear maps. There's all kinds of interesting quaternionic analysis around that. You can like develop a version of the Cauchy's theorem, Taylor expansions, and so forth, which is very useful for the analysis of the nonlinear, the version of this equation from a manifold. Okay, and then so I said this was from R4, but I can make it invariant in the kind of direction of E0, 1 in the quaternions, and then you get sort of similar equation. Okay, and then I just want to notice here there's the sign difference. Up at the top you have a minus, and the bottom you have a plus. So that's because we wanted to use holomorphic curves rather than holomorphic. And so that is some tension here. There's some way of, you could have to, if you really want the equation to be like this kind of equation, which you do for staying sane, then you have to fix the conventions a little bit, which we discussed a little bit in our paper. Okay, so anyway, let's just say, I'm just going to draw some pictures, and we'll try to move on to more substantive stuff. So this 2 category should have objects complex Lagrangians, 1 morphisms intersection points between the complex Lagrangians, if they intersect transversely. More generally, it's not clear in full generality. Like I'll say what I can understand. And the model case is this case of a kind of a finite dimensional complex Morse function, where again it's not really clear how to define this category for like a general complex function on an affine variety set. And then the one morphisms, anyway, in the Morse case should be intersection points, and the two morphisms should be these Floer strips between them. And then the differential in the composition should be given by Fueter maps with these holomorphic Lagrangian boundary conditions and these Floer strip asymptotic conditions. When you apply Hochschild homology,
sorry, I somehow missed these foundational questions with the Fueter equation, like existence of solutions and blah blah blah. Is it are they resolved?
There are lots of foundational questions which are not resolved. There are some which can be done. So, for example, like no one has written down some kind of statement about local existence. That's the analog of like, so if you haven't prescribed the jet of a, this is like, I can say as much as you want about, I think I know the state of the literature. So the hard problem that no one's resolved is the compactness theory, which is if you have a sequence of solutions to the Fueter equation, what are its, if you have some energy control, what kind of limits can you get? So, in the hardest version of that, like you could make it, if you have these very non-compact boundary conditions, this is at least as hard as the complex gradient equation, for which we already don't know that the Gray-Otomor-Witten proposal is correct. But, in some modified versions of it, you can kind of, the hard part is really this kind of interior bubbling, sort of what if energy concentrates at a point? And that's generally not resolved, although in a couple of cases, you can a priori exclude the interior bubbles. And I can say something about maybe hope for, in certain cases, understanding these interior bubbles. But then there's easier things, like, it mentioned existence of solutions. So, for J holomorphic curves, there's a local existence theorem. So through every point, there's like a J holomorphic curve, and you can prescribe the holomorphic part of its jet. So that, for example, has never been written, but it doesn't seem terribly difficult. On the other hand, global existence theorems, well, if I give some complicated Lagrangian boundary conditions, whether there's a J holomorphic curve with those Lagrangian boundary conditions or not, that, there's no general theorem. So you similarly can't hope for that in the Fueter sense. But that, there you can maybe get conjectures and then try to like use category theory to force solutions or use adiabatic limits to force solutions. So I'll mention something about where you can show there are some solutions to the Fueter equation. Okay.
Mm-hmm. Yeah. Okay.
Great. Yeah. Okay. So here are the pictures. These are sort of the pictures for just the two category. So if you have, two objects, these are on the bottom, holomorphic kind of Lagrangians, then you can have maybe two morphisms, one morphisms between those Lagrangians, and those are objects in this hom category, P0 and P1. And then you can have a two morphism, which is a morphism between morphisms. So it's a morphism in the hom category. That should be given by a holomorphic strip. And the theta you use here is the theta which, if you apply the symplectic action functional to these two intersection points, then they project to points in the complex plane, and you use the theta given by the straight line between those two things. So these strips will project to straight lines in sort of the plane of the complex action functional. And then the composition between holomorphic Lagrangians should be given by some holomorphic triangles. So something that you can conclude in this Morse case, that's just not very many of these. These will basically always be constant. So which holomorphic triangles you should use is you should use the ones that come from the J theta bar, where the bar is the one from the background angle. At least that's one way that I can see of making the whole structure into a consistent two category. It's interesting if you can, I don't know if there's a modification of that, or maybe you count somehow these J holomorphic triangles for all the J thetas at once. I don't know how to make that into a consistent two category, but there's one prescription where you use the back, to fix a background angle for the whole kind of hyperkahler manifold, and then you use that background angle for all of these Fukaya-Seidel categories, and that's how you use to define this composition of two morphisms. So then when you apply Hochschild homology, you'll recover the Fukaya category of a particular symplectic manifold. Okay. So that was kind of comment for those who have thought about this. And then, there should be horizontal and vertical composition, so you can compose within the hom category between two holomorphic Lagrangians. So then, what you should do is you should put boundary conditions like this. So you kind of think of the whole domain as C cross 0, 1 of the Fueter map. And then on the left-hand side, you basically, you think of everything as like the previous picture with complex Morse theory, but crossed with an interval. So now this kind of going up and to the left, well, you get this real line cross this interval. So that should be a holomorphic strip, and that should be this holomorphic strip U3, and so forth. And then up at the sort of the interval at 1 or at 0, you put the holomorphic Lagrangian boundary conditions. So that's the kind of way you would compose within a hom category. And then similarly, this is sort of, at least formally, you really have, I mean, it's clear from this kind of picture how you would set up the boundary conditions, but this is how you would compose sort of between two morphisms between hom categories. This is kind of horizontal composition of two morphisms. Okay, and one interesting algebra question is, okay, well, so can you use these sorts of pictures to get some kind of like version, explicit model of an infinity 2 category? So, clearly what I drew is like just kind of something for a 2 category, but if you really, there are chain complexes everywhere and you want to show that kind of the whole structure is there should be some coherent version of the structure, there should be some model of an infinity 2 category, but there's kind of there's some connection between these sorts of pictures and maybe explicit models of infinity 2 categories, but that's like an interesting direction if to kind of think about if you want to think about the connection between kind of TQFT and algebra. Okay. So anyway, so here's the status of a hard analysis. Much of this is difficult to make rigorous, except in a couple cases. So the basic problem is that if you have a sequence of Fueter maps, then their energy, which is the integral of basically the L2 norm of the derivative, can concentrate in certain regions. And in the case of holomorphic curve theory, which is a lower dimensional analog, we know what happens. You bubble off holomorphic spheres. So here you bubble off something still in codimension 2. And sorry, this should be codimension 2 and 3 in the bottom. And the codimension 1 locus, well, the generic point of a codimension 1 locus is going to have a tangent vector, although in general, we don't know that. And then kind of that tangent vector specifies a complex structure on the target, and transverse to that, you bubble off a J holomorphic sphere with respect to that complex structure. And then in the codimension 2 locus, well, we kind of don't know what happens if there are codimension 1 pieces hitting that the codimension 3 locus. We don't know what happens if there are codimension 2 pieces hitting that codimension 3 locus. But if there are none, then you could do some kind of normal rescaling. You look at radial coordinates, and then you see that you bubble off an anti-holomorphic section of this twister fibration. And so that's kind of all that's known. And you can exclude bubbling a priori when the target is flat. That was used by Holak and Solomon to kind of study similar equations for a couple manifolds. And then, there's a recent paper, or there's a recent announcement of like showing that you sort of can exclude this sort of bubbling for the Atiyah-Hitchin manifold, which is an interesting hyperkahler manifold. And this really uses like the fact that we know everything about this manifold, basically. It's not really clear whether these bubbles actually happen in important examples. It's not really clear how you would incorporate them into the algebra. I'll say something about, from my work with Aleksander Doan, we think we have some class of manifolds for which we can exclude all this bubbling. And, maybe some tools to help exclude this bubbling in other important cases. I kind of think of the sort of understanding this sort of bubbling in general, kind of in more detail than this, is pretty hard. But I think in cases where like the target is some specific manifold, it should be much more restricted than this, and one should use the explicit geometry of that manifold to control this stuff. Okay. So this is the thing that really stops the development of this theory in kind of full generality. The rest of the issues are much more tractable, I would say. Okay. So now something I just want to say. So there's this story that, so if I mentioned that these J Theta holomorphic strips, they project as straight lines in the kind of values of the symplectic action functional. So in particular, for generic J Theta, these J holomorphic strips don't exist. So what that means, and there's a generalization of this theorem, that for generic J Theta, there's no J Theta holomorphic polygons between any pair of smooth complex Lagrangians. They don't have to intersect transversely or anything. And so, one reason why this kind of story might be appealing is because, well, if you look at the usual Lagrangian Floer theory of these two holomorphic Lagrangians, for any one of the equatorial symplectic forms, then it shouldn't be very interesting in the sense that it shouldn't count any kind of non-trivial holomorphic disks, holomorphic strips. And that should be given by this sort of some topological invariance, some kind of hypercohomology of some perverse sheaf of vanishing cycles in the intersection, at least when the Lagrangians kind of don't intersect at infinity, and you can prove that. If they do intersect at infinity, then I don't know. I mean, then they're going to be very sensitive to like how you perturb the Lagrangians away. to not intersect in infinity. But this isomorphism should depend quite a lot on theta. And the reason for that is because if you think about this sort of theta, remember this is, from this perspective of complex Morse theory, this is like the direction in which the Lefschetz thimbles are going. And so as you vary theta, you should get a bunch of interesting transformations of this map. So you can formally see that there should be some Floer theoretic continuation map where you just solve the continuation map equation for varying theta. That gives you some interesting automorphism of this group on the right. And then on the group on the left, there's this sort of thing from algebra, this sort of monodromy of the Purushiva vanishing cycles. And these in general should be different. And their difference should actually be a count of these non-trivial holomorphic strips. So that's like the smallest shadow of this sort of story. And that operator, the difference between this sort of algebraic monodromy and the sort of Floer theoretic monodromy is supposed to be the Stokes datum for this path integral that was studied by Complexification and Saulinas. Okay, so that's some stories. So now let's get to what we did. This is some sort of very simple adiabatic limit computation, but it suggested lots of interesting things to try. So why did I? So what's the sort of? I mean, the basic principle in Floer theory is that the simplest symplectic manifold is a cotangent bundle, and a cotangent bundle gives a local model for things in general because it gives some kind of finite dimensional reduction of these infinite dimensional Morse functions. So what Floer proved, the simplest computation of Lagrangian Floer homology, is that if you look at the zero section and the graph of the differential of a C2 small Morse function from the zero section to R, the graph of the differential is like a Lagrangian submanifold of the cotangent bundle over that base. And he showed that the Lagrangian Floer homology between these two Lagrangians is the same as the Morse homology of that function. And in fact, that's like a very strong statement. What he actually proved is that there's just a bijection between gradient flows of this function and holomorphic strips between these two Lagrangians with respect to some specific almost complex structure. And that specific almost complex structure, it's kind of constructed so that it's the same as solutions to this equation on the bottom right, the same as solutions to this equation on the bottom left, where this J comes from the metric on the base. If you have a metric on the base, you get an almost complex structure on the cotangent bundle. And then basically, you do a couple estimates and you show that this DTU term is just 0 when F is C2 small. That's what he did. So that's the sort of the local model, holomorphic strips between two nearby holomorphic Lagrangians. Holomorphic strips between two nearby Lagrangians are, at least for a certain complex structure, the same as Morse trajectories. And then, you start showing that you don't need exactly that complex structure and so forth. Okay, so what we did is we tried to complexify this setup. So if you have a complex Morse function, but so to make sense of it being a C2 small, we're going to ask for it to be a Stein domain. That's a manifold boundary. I'll say a little something more about how you can maybe deal with that later. So then, you have this I from the base on the cotangent bundle. You have this J from the metric, that's some other one, and they'll satisfy the quaternionic relations. And so Floer's theorem says that real gradient flows of this complex Morse function F are in bijection with J Theta holomorphic strips between these two Lagrangians, the zero section and the graph of the differential of this holomorphic function. So what we did is we showed that there's kind of for basically the this is JT, which gives you the corresponding KT. It's Floer's JT. So for that JT, there's a bijection between the complex gradient trajectories of this function F and Fueter strips between these Lagrangians with these sort of boundary conditions for. And so what this suggests is that there should be a complex analog of Floer's theorem, which is the hom in this Fueter 2 category, this conjectural Fueter 2 category between the zero section and the graph of the differential of a holomorphic Morse function should be the Fukaya-Seidel category of the holomorphic Morse function. Okay, so this conjecture at this point sort of seems tractable because the right-hand side is, at least there is a model of it. You have to change, the equation a little bit, kind of use this like Hadish-Donghao method. And then the right-hand side can be made sense of. And then, there's corresponding analogous things you can do on the Fueter side. And much of that and these estimates are pretty, they can be, it's not a crazy modification to do. This conjecture seems, tractable, but it hasn't been done. And then, okay, so here's one thing I want to say. This is something I'd maybe love to hear from someone who's at this talk later. So, one motivation for this whole story, so like why Hadish did this, is because, there's a bunch of interesting complex Morse functions. For example, the complex Chern-Simons functional, which is just like if you have a connection on a principal bundle for a complexification of a compact Lie group, and there's some natural holomorphic function in the space of such connections. And then,
you kind of, I mean, when you speak about on some very general level from outside of the Earth, that's okay, but there is no Chern-Simons functional. There is only well-defined holomorphic one form.
Yes.
So you can, of course, make things difficult and go to the universal cover, but it's not just a space of connections. It's something more complicated, and it's a stack. So you see something is missing. So when you say at this level, as people spoke like 30 years ago, this idea for conjecture, blah, 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 yeah, but when you want to be more precise, you probably nowadays you should be a little bit more careful. There is
I agree with you.
There is no holomorphic function, and you didn't tell us what to do if you don't have a function.
Yes.
Yeah, so that's a bit a problem. For example,
yeah, so one
do
interesting...
you know what to do with a holomorphic one form?
Yeah, so one interesting challenge that I think would be good to do would be to carefully explain how you deal with the Fukaya-Seidel category of a holomorphic one form and how you would do the corresponding complex Morse theory. And the natural thing to do is you want to just say you go to the cover, but then you notice that there's some symmetries of all these operations. And so you shouldn't need like quite so many different objects. Yeah, so that's, I think, a basic thing. And a different, I mean, no one's written that down, say, or seen, fast checked if there's like kind of extremely incomprehensible problems or not.
Yeah, but even before you categorify anything, just what
I mean, Morse-Novikov theory makes sense. That's that Novikov theory is.
Morse-Novikov theory makes sense, but holomorphic Morse-Novikov theory, it's a different story, as you mentioned at the beginning. If everyone models with a holomorphic Morse theory as a sort of a zero level of understanding, like complex Morse theory, yeah. Now, complex Morse-Novikov theory, kind of.
Yeah, so I agree that that's an interesting project.
Yeah, but it's a project. It's done.
Great.
Yes.
Where is it? I would love to see where this. My impression is that this is something that has been kind of in the community, but I don't really know anywhere where it's written. So that's good to know.
Okay. All right. Yeah. Okay. Go ahead. Yeah.
Anyway, this is sort of a request. So I mentioned basically that. So one motivation for this whole story is some people noticed that when you look at this complex Chern-Simons one form, then its real and complex gradient flows reproduce other interesting PDEs. And there's this sort of very heuristic Atiyah-Fleur type conjecture that this sort of Fukaya-Seidel category of this complex Morse of this complex Chern-Simons one form should be some kind of hom in the Fueter category between two holomorphic Lagrangians in the complex character variety with respect to specific complex structure. Well, applying Hochschild homology to that, you would get that some kind of instanton Fleur homology of the complex gauge group should agree with a real Fleur homology group of these complex Lagrangians. And then this motivated some construction of Abuzaid and Manolescu, where they basically, use this perverse sheaf ansatz for this group and check that it is independent of the Heegard splitting. But already there's like lots of kind of confusing differential geometry. For example, there's this kind of question of like how these Lagrangians intersect at infinity. So that's somehow related to the questions about Z2 harmonic spinners. Also when you actually take this adiabatic limit, you get an interesting perturbation of Fleur's equation on the right. I don't really know if that's ever been kind of investigated. So even like in kind of the correct formulation of a conjecture like this, even at a very basic level, I think it's sort of interesting to play around with the differential geometry. But separately, anyway, we mentioned there should be some kind of monodromy automorphism of Hochschild homology of a Fukaya-Seidel category of a complex Morse function. So that should this Abouzeid-Monolescu invariant should have some endomorphism, which actually counts non-trivial holomorphic curves. And that should be some kind of Stokes datum for the complex Chern-Simons functional. So supposedly there are people who study this, and I would love to understand whether people who study this kind of actually give predictions for like counts of holomorphic strips and whether those can ever be checked. And then in some other cases, at least recently, there have been some announcements where you can compute this, some of these counts of these exceptional holomorphic strips for certain complex integrable systems using kind of techniques involving scattering diagrams and so forth. This is some work
this approach via resurgence, actually, I will be speaking about that tomorrow at Perimeter and on Monday at the University of Toronto. It's kind of, it can be made precise, and it allows people to avoid this hard analysis. Actually, but it's kind of a general comment. It's my understanding that you need these two categories for some more serious reason than just complexify, if you like, Fukaya-Seidel category. There is probably, it's later on your slide, something about 3D unequal 4 theories.
Yeah, that's the biggest reason. But I would actually just like interesting computations, and it's not easy to find them. So even for like specific Lagrangians that are not in cotangent bundles, basically actually computing like the sort of shadow of the structure is already
there is
and it would be great to really verify those in some interesting examples. That's
first of all, they never sits in the cotangent bundle. For example, in Gukov and other story, they have gauge group SL2C and they sit in C star square, which is not a cotangent bundle. It's rather open part of a toric variety.
Yes, I understand that the physics predictions don't come in cotangent bundles.
All right, and indeed you can in the complexified Chern-Simons theory you can avoid these difficult questions, which like about compactification at infinity. You can work with a local data, then incorporate indeed these Stokes indices, at least in the Morse case. Otherwise, it's perverse sheaf of vanishing cycles. And then, but this is the beginning, because it's like in this algebra of the infrared story, you have critical points, and then they start to interact with each other by computing this gradient lines, blah, blah, blah. But the point is that then you can consider the local formal expansions at the critical points in Chern-Simons theory and make the Borel transform. And so then it becomes a germ of a complex function on, I would say, on the Fourier dual plane. And so you start analytically continue. That's the idea of the resurgence. And so each critical point give you a branch of a multi-valued function. So altogether, they are combined in a single multi-valued holomorphic function, which contains all the information about Chern-Simons. Now, if you want to think of that categorically, you observe that this function is more or less the same as kind of a perverse sheaf of infinite rank with infinitely many, with countably many singularities on the dual plane. So then you categorify this sheaf, because the whole story of the algebra of the infrared algebraically just categorification of the direct image of the constant sheaf with respect to this Landau-Ginzburg superpotential. So, and you want to categorify this. So you have local Fukaya-Seidel categories which somehow interact, blah, blah, blah. So now you have to do the same thing, but in a much more complicated situation when your perverse sheaf has an infinite rank, and differently from Landau-Ginzburg model, it has infinitely many singularities. So that's really a challenge, but it's possible to do it, at least conjecturally, in more or less the same way. Like
Sure.
Yeah,
My question is very simple. There is a number of flow lines between two of these critical values in certain cases, and there are predictions for it, and I would like to see these flow lines. That is kind of what I would like to see this in some interesting examples. That's all I'm saying here.
Yes. In this sense, you are right.
I would like some like nice worked examples of this.
But you do not need. That's an important point is that you do not need infinity. You do not need any estimates on how some, I don't know, pseudo-holomorphic disks or their three-dimensional analogs, how they behave in the when you approach the infinity of your space. Because the basic idea of Heidi's and Gayota, Moore, and Witten is that you work with local data, and with this
I would love to discuss this point with you.
All right. Yeah, okay.
I think I largely agree with you. I think there's a couple subtleties, but they should only arise in maybe more complicated settings. I would love to talk about that sometime. Yeah, cool. Anyway, so now let's go back. Anyway, I was just saying, like, I'd love to see more kind of worked examples of all these ideas, because some of these ideas are standard, but really getting them kind of worked out in sophisticated examples is pretty challenging. So one thing I wanted to mention is that, so I did some computation about Fueter maps into the cotangent bundle, but cotangent bundles aren't hyperkahler. I mean, there's a small hyperkahler metric maybe near the zero section, but it's incomplete, produced by Clayton. And so that thing doesn't really kind of work analytically so well. So our perspective is that, like, we don't really need a hyperkahler structure, and we're not sure exactly what you need. What you need is three kind of action of the quaternions and then some energy identities. So these cotangent bundles, they have these taming triples of two forms. I'll show you what they look like in a second. And then that thing gives you energy identities. So this category kind of doesn't obviously need like hyperkahler manifolds. It should have some kind of weak hyperkahler manifold. That's the target. I don't know what that exactly should be.
Is there an analog in this hyperkahler world of bounded geometry, which people actually use?
There is an analog of bounded geometry, but even for holomorphic curves, bounded geometry, that's something about kind of infinity, and that doesn't give you energy estimates in the interior.
Okay.
So there's also, you actually need a taming symplectic form. So this is the analog of a taming symplectic form. It's the same kind of mathematics. There's a quaternionic analog of that theory.
Okay.
So, and part of that, I mentioned that you have the Stein domains. We cut off infinity, but how would you deal with the whole Stein domain where you want to use some convexity principles? So there's this kind of maximum principle for J holomorphic curves. So it turns out that there's a similar maximum principle for Fueter maps. So we write down what it is. And there's an analog of like an IJK convex function, which is some function so that some 3 form is positive on some linear maps, basically. So then it satisfies the maximum principle. And these taming 2 forms are the kinds of 2 forms that arise here. So basically, you have some categorical idea. You start trying to prove like expected analytic thing, and you come up with some new analytic notions, which are kind of interesting and maybe useful for studying like compactness. So for example, you can use this idea to define the kind of analog of a Weinstein domain in symplectic geometry, but in the quaternionic world, which is just as an IJK manifold with one of these IJK convex functions. And these things somehow behave like quaternionic analogs of Stein domains. So for example, they kind of have homotopy types of quarter-dimensional CW complexes. You kind of exhaust the space of homotopy types. And I don't know, it's just an interesting notion. I don't know exactly like how much invariance this has, or like whether these things have H principles, but at least the point is the cotangent bundles of Stein domains are quaternionic Weinstein domains. And we sort of tried to compute something about this Fueter 2 category of this cotangent bundle of a Stein domain. Okay. So unfortunately, my kind of time is up, right? So I can't really continue.
Yeah, but since unfortunately also for you, the word mirror symmetry appeared on the slide, so you should really say something, because many people in the audience are interested in mirror symmetry, maybe in 2D.
Okay, so let me do
context,
that.
But,
so,
yeah, okay.
So there is this whole story now of 3D mirror symmetry, which is supposed to be some kind of duality between these 3D n=4 gauge theories and maybe 3D n=4 sigma models. The gauge theories you should think of just as sigma models into some quotient stack. And then these 3D n=4 theories have some kind of A-type and B-type twists. And then the category of boundary conditions, this A-type twists should basically be this Fueter 2 category. And the category boundary conditions of this B-type twist should be some kind of something, well, related to the Rozansky-Witten model. And that thing was kind of developed by Kapustin-Rozansky and Saulinas, at least in part. So neither of these have kind of been like made totally clear in like full generality, but certainly the sort of the B side kind of behaves like the B side, so sort of more algebraic, because there's sort of none of these huge confusing instanton corrections. And so at least it's better developed. So now one thing you get from this kind of picture is that, well, so these A-type gauge theories, sometimes you should relate these Fueter maps to sort of Fueter maps into some kind of GIT quotient. This is something that is an analog of what happens in...
I somehow, I'm not really a physicist, but I don't know what is A-type gauge theory, because from my understanding, there is a gauge theory, and there is its A-twist, which is topological theory, and there is a B-twist, which is also topological theory.
Right,
so
but when
I have no
say,
idea.
Yeah, so
A-type
the Seiberg-Witten equations, I think of as, you know, it's like a math. So that's something that mathematical gauge theorists study, like people who do an analysis around gauge theory. And I think of that as an A-type gauge theory because it comes from the A-twist of this kind of full supersymmetric theory. So that formally it's a TQFT, but you know, to define it, you have to study the solutions to some kind of interesting partial differential equations. So other people would call those partial differential equations the gauge theory.
All right, so on the A side, you have to do some hard work, and on the B side, you just enjoy your life. So
maybe, I mean, this is, yeah, to you at least it's easier. I mean, this Kapustin-Rozansky-Saulinas two categories still doesn't have like perfect foundations. They kind of make sense on things which are kind of like cotangent bundles.
No. I mean, even the Rozansky-Witten theory is not defined as a 2KFT, so it's kind of even at the level of one category, very little is clear.
Yeah.
All right.
So anyway, the hope is that these gauge theory type equations you should be able to take some kind of limit, and you should get Fueter maps into some kind of quotient and some nonlinear map, some kind of nonlinear manifold. And you know what this quotient is. This quotient is called the Higgs branch of this gauge theory. It's something you can write down. And then, so this 3D mirror symmetry has all these expectations. It should exchange the Higgs branch and the Coulomb branch. It should exchange the A twist with the B twist. So from that, you should exchange the category boundary condition, A-type boundary conditions on the Higgs branch with the category B-type boundary conditions on the Coulomb branch. And then this is an interesting way to try to get a handle on like when you have solutions to these sort of nonlinear PDE, these Fueter PDE. And these are often pairs of sort of famous hyperkahler manifolds. And on the left-hand side, if you take Hochschild homology of this two category, you should get the some kind of Fukaya category. And in many cases, you know what that Fukaya category is, because like these Higgs branches are often objects of kind of geometric representation theory, basically. So here's one example. I'll just say something about this and then I'll stop because maybe people are still listening. This is a funny example. So this is a T star C star. So I'll say something about how you use this kind of idea to get some analytic predictions, which seem to be true. So I'm told, you talk to physics types, this should be mirrored to T star B C star. So that's a point mod C star. So then the Fueter category of this should be the same as the Kapustin-Rozansky-Saulinas category of this other guy. And this latter thing is a cotangent bundle. So this should just be related to sheaves of categories on the base. And so, the basic thing to remember about these Kapustin-Rozansky-Saulinas category is that it also has objects complex Lagrangians. And then if the kind of the morphisms are locally modeled on, some mild, okay, this is not exactly correct, but a certain mild modification of matrix factorization categories. So holomorphic Lagrange is locally the graph of a holomorphic function over the base. Oh, sorry, two nearby holomorphic Lagrangians, one looks like the graph of a holomorphic function over the other. And so you look at kind of locally the matrix factorization category of that function. And that's sort of the B-side analog of this conjecture that we had, that this sort of the HOMs of the Fueter 2 category, locally the Fukaya-Seidel category. Okay. And so in this case, you think about what this should be, and this should be something very simple. It should have one object, and its endomorphisms should be Z with no morphisms between them. Right? I'm not an expert on this. This is maybe I'm taking this from other people, from like Hilburn and Gammage. But this sounds kind of boring, but you can kind of see what this is on the A side. On the A side, you need to introduce wrapping, which is an interesting operation. So here you kind of just add a holomorphic Hamiltonian to this action functional everywhere. And what you do here is, well, it's a cotangent bundle, so you do kind of complex geodesic flow on this cotangent bundle. And then if you do that, then basically all of this seems to work out. So you look at like the self-homs of this Lagrangian, these are some holomorphic strips, you compute what they are, and you see there's an integer's worth of them. So then you shouldn't have any holomorphic strips between these kind of complex Hamilton chords, and that seems to be correct. And then similarly, you can look at some kind of category on the loop space. So you kind of look at the Fukaya-Seidel category of the action function on the loop space of your thing where you've forgotten the Lagrangian boundary conditions. And then you can get a prediction for what that category should be using this kind of conjecture. You use some kind of two categorical trace, you chase through it, and you get that this should be Z mod C time. This is this kind of algebra. And then this kind of modules or sort of Z copies of modules over this algebra. And on the A side, you see what this should be. So the closed trajectories are lots of kind of disjoint copies of C star. It's a Morse bot action functional. And then, well, this Morse bot complex kind of Morse theory can be made sense of. You basically kind of say the objects, the Fukaya categories of any one of the critical loci, and then the morphisms are given by still real gradient trajectories between these Lagrangians inside complex critical loci. And that basically works. So then from this, you should get that there shouldn't be any morphisms. So I've also been so basically no solutions to this equation on cylinders, but these asymptotic conditions. And I've also been verifying that. And if that was true, then you get basically the proper objects of this B-side loop space category. Okay, so that's kind of interesting. That's a bit of kind of somewhat, this looks very different from this. This is like some kind of Hamiltonian flow, but they seem to be connected.
Yeah, unfortunately, it's impossible to understand anything at this speed. And yeah, I would personally prefer that you start from the end. I mean, start with this example and explain it in detail, but unfortunately, it's probably too late to make that correction.
Yes, I don't know kind of where to start the story from.
Yeah. You start with some basic stuff, and so unfortunately.
Yeah, but this is some kind of basic example, and it's maybe the thing to say is basically if you have like the cotangent bundle of a complex group, then you can try to study complex geodesic flow on it. And there's an interesting holomorphic symplectic form on this manifold. It's the generalization of dp d log q. And then, this is an interesting, the geometry of this complex geodesic flow is already kind of interesting and seems kind of related to these sorts of more B-side ideas. That's the sort of moral here. And you could try to generalize that. So the next example would be T star P1, for example. So that's kind of, maybe you can think of that as an unwrapped version of T star C star. There's some predictions for what that should be. That should be related to this principal, there's decategorification of this should be this principal block of category O for SL2. And, I don't really have any good evidence for that, except there's some local models. You can break it up into pieces, kind of north half and the south half. And there's like at least kind of a detailed description of what this categorification should be. And it's interesting to try to find these holomorphic curves in these Fueter maps. So you do some very explicit thing, like find this curve for this kind of holomorphic function. That's where the status of this is. I would say it's that, there are explicit curves that someone needs to find, and a couple places you can verify that maybe the curves that shouldn't exist don't exist, and trying to find the curves that do exist is sort of a research topic. So that's maybe all I should say right now, except that the biggest question for me here is that theoretically, if this is some 3D TQFT, then you would like things to have monoidal structures. But I don't know how to define these monoidal structures, because these functionals are usually not Morse. Sometimes they're Morse bot. In the Morse bot case, I don't know how to define the endomorphisms of a holomorphic Lagrangian, like to define composition on that. And I think that's a really interesting question. Okay, so thank you. I'm happy to chat about whatever, but that's maybe.
Yeah, all right. Thank you very much. So you kind of should be awarded a special medal for explaining 56 or whatever, 50 slides in one talk. Yeah. All right. Now, are there any questions? Yeah, it's indeed a lot of. Yeah, a question?
Yeah, can you go back to the log for a category? part.
Zonju, can you speak louder? I don't
Yes,
hear.
can you hear me?
Yeah.
My office.
Go ahead.
Can you go to the loop category, which you were describing
Yeah.
very best? That looks to be.
Which one? So this is the algebraic one, and this is the geometric one.
Yes, this the algebraic one actually. So here those are the those are Hochschild's the double H.
Yeah. So if you have a two category, there are two things you can do to it. One of them, you can take Hochschild homology of each Hom category. The other thing you can do is you can do this kind of two categorical trace. So there's some paper of Gates, Gorey, and collaborators, and there's another paper. I'm happy to send you the references. I'm sorry, the references are correct in my paper with Alex. I mean, I explain where to look for this. But this is like, a two categorical. It's basically the endomorphisms of this two category inside the two category of two categories. That's a one category. That's a completely different thing from taking Hochschild homology of each category. So it's the latter. Okay, so it's that kind of version of Hochschild homology.
And that is at the end, which is equivalent, assume, to the graded category of modules of the Laurent polynomial rings.
So in this case, so we look at the KRS category of T star BC star, and my understanding is that that's the same as the coherent sheaves on this kind of derived loop space of T star BC star.
Okay.
And that you can compute. That's just a classical variety. Well, almost. It's like a C star modulo the conjugation of C star on itself. So that's a C star cross a point mod C star. And that's this thing on the right. That's what this computation is.
So that at the very right looks to be the Z cross that basically just all the Z graded object version of the category.
Yeah, that's right. So it's a relatively simple thing.
Okay.
Yeah, it's Justin Hilburn told us about some similar.
Yeah. I mean, this was, I was talking to him and we were trying to think of like, when can you guys give me like the simplest prediction? And also there's this problem about wrapping. And this is a setting where it seemed like you would need to wrap. And so I wanted to like get a model, because this wrapping problem is like, if you have a kind of a complex symplectic manifold, well, it usually is non-compact. And we know from Floer homology that there are different ways of treating infinity. And so the natural way of treating infinity in different ways is you can choose different holomorphic Hamiltonians, which tend to not be small at infinity. So they'll change the category. And so I wanted to have a model where like kind of there's a lot of wrapping and it's clearly important. And so this is sort of an example of that. So on the A side, this wrapping is like necessary to get counterparts to this.
And so in that case, the Z indicating how number of times it ramps.
That's right.
Okay.
So there's if you look at the time one Hamiltonian loops for the complex Hamiltonian, then they're indexed by the number of times they wrap during that time, during that period. And obviously you can start at any point of C star. So as the momentum goes up, you wrap faster.
And also at the very end, you mentioned about the monoidal structure.
Yes, so this is a question for me. So formally, when you say you have a TQFT, then for example, this thing, so if you have a 3D TQFT and you evaluate it on a circle, then you should get a monoidal category. That's something that people say. And it's kind of clear that's related to these kinds of horizontal composition pictures that I drew, right? But those made sense in the Morse case, but I don't know how to make sense of them in like even the Morse bot case. So I think that's an interesting problem. So here you can like see what the monoidal structure should be, although I haven't thought about it. I mean, I think you just kind of add in this copy and then like tensor in this thing. But I don't know how to find Fueter maps here to like manifest that. But this is at least a model where we can try to figure out what the general pattern is.
When you say monoidal, you mean in some infinity sense? Or...
I mean, in the fully general sense, yes, you would need something infinity. But obviously, you can just take homology everywhere, then you would have an actual monoidal category.
Yeah, I mean,
So
yeah, it's
I'm already
very
happy with the,
difficult.
understanding the simplest piece. Like before understanding all the coherences, let's understand what the monoidal structure, like how do you take, so, if you get lucky and all these more complex Morse functions, these action functionals are all Morse, actually, then it's kind of clear what to do with these Fueter maps. But if they're not Morse, I don't know.
Yeah, let me ask you.
So I think that's an interesting question. Here are some examples where at least we know there's a monoidal structure. We know what it should be. Can we realize it using Fueter maps?
Yeah, but let me ask you this question. So for conventional Fukaya categories, you can sometimes, rarely, but sometimes can avoid this difficult analysis by replacing the category by something defined in terms of constructible sheaves, like this Nadler-Zaslav approach to Fukaya categories. So in this case, I mean, sometimes it's easy to define to see the monoidal structure when you work with perverse sheaves. So that's what I mean. Your two category, it's modeled by, let me say, by Fukaya type of construction. So you honestly use this holomorphic Lagrangian, the analog of pseudoholomorphic disks, which are kind of more complicated objects, but nevertheless, it's kind of what people with symplectic background would do. But either an analog of this Nadler-Zaslav story, which actually well understood in the case of the cotangent bundle, but there should be some probably similar, yeah.
I don't know because, again, in the cotangent bundle, it seems that the local model is given by the Fukaya-Seidel category of a holomorphic Morse function. And I don't know how to define that Fukaya-Seidel category using algebra. Like, technically you can do another reduction, right? So now on this holomorphic function, I guess maybe you can do something. I haven't thought about this until now. So this is a nice question. So, the Fukaya-Seidel category of a holomorphic Morse function on the base is, of course, some kind of sheaf category. Because, you can give it, the base is, if the base is Stein, it's also Weinstein, and you go to stop. And then now there's some skeleton of this thing in the zero set, which is, this is related to some category of sheaves on the skeleton.
Yeah,
so maybe you can get a distinguished skeleton by basically choosing a pluri-subharmonic function on the base. We have to use that kind of thing in the analysis anyway. So maybe then it's possible to guess what the monoidal structure should be. That's interesting, but I haven't tried to analyze that kind of construction. I mean, we are basically taking these adiabatic. We've taken kind of one adiabatic limit. We could try to take another adiabatic limit. And then maybe that'll all be kind of sheaves on this zero on this the skeleton of this. That's an interesting idea. It's interesting to try.
Yeah. Okay. I also have a question to your very last slide, since I kind of browse all to the end. You mentioned that your very last remark is that if you look for BFN construction, it gives infinite dimensional rings. I do not know how that story is related to Seiberg-Witten invariants, but in some other situation, actually related to this Gukov and other papers which you mentioned earlier, you can construct invariants by taking the character. I mean, you have some infinite dimensional ring, that's all right. But in case if you have an action of the torus, you can take the character of this space, which will be, generating function as many variables as the dimension of your torus is. And so this can be thought of as invariant. It's a refined invariant. It's physicists often use. So I don't know whether it's relevant or not.
I think it might be relevant, and that's a very interesting question. So the reason the BFN construction, one thing that is sort of part of the motivation that's given for the BFN construction is that this should be like whatever, the relevant multiple spinor cyber. So this multiple spinor Cyber-Witten theory, or whatever, what do they say? They have a compact Lie group, you choose a quaternionic representation, and they give you some ring. So what is that ring that's supposed to be? Well, the quaternionic representation is a hyperkahler manifold with a gauge group action. And so you look at the gauge sigma model and you do its A-twist. And then that ring is formally what that A-twist should assign to the two-sphere. The two-sphere, whatever. That's kind of the motivation of that construction. But, there's some gap because, then, for example, we know what, like Cyber-Witten, like the actual Cyber-Witten equations actually assign a ring to the two-sphere. I forget what it is, but you can compute it. And from that, you can, using this usual TQFT formalism, compute the sort of 3D Cyber-Witten invariant of a 3-manifold. And I don't know how that's related to whatever their ring does, because their ring is infinite dimensional, and so it's not obvious what you're supposed to do. I've been told that this maybe has something to do with like this deformation, this kind of extra parameter in the Cyber-Witten equations. But I think it's just an interesting puzzle for me. Like this BFN construction has this differential geometric motivation, and then it's supposed to be about what, these exactly solutions to these equations, but then there's some kind of disconnect, even in the one case where like we really have great analytic control over these kinds of equations, and we also understand the algebra completely.
Yeah, but Semon, there was, before BFN, there was just N, because Nakajima wrote some very inspirational, I would say, paper, I think in 2015, something like toward mathematical definition of equivalent branch. And inside of that paper, he has sort of a very analytic, I would say, proposal. And in terms of a certain functional sort of a generalization of Chern-Simons or whatever, it depends on the taste. And it was never made precise. I spoke to Nakajima. I liked it very much because it's in the spirit of our work with Maxim on cohomological whole algebras. But he told me that he could not fix analytical difficulties. So did you look at that paper?
I have looked at it. I think this question of like maybe turning back to that question now that we're better at some of this analysis is a compelling problem for people who are kind of interested in the boundary, kind of giving more differential geometric foundation to these more analytic constructions, or more algebraic constructions. Because now, for example,
really love to have this.
There are a bunch of interesting kind of Kobayashi-Hitchin type correspondences, which suggests kind of maybe a cleaner way of understanding what went wrong. And so I think there's like some hope for doing this. But a good test case, I think, for like, did we get the right answer is, the Cyber-Witten TQFT on the analytic side, like the usual Cyber-Witten TQFT, is really well understood. And then we also have that, whatever Nakajima says he assigns, but there's some kind of a disconnect between that. That's like a concrete place to focus in on, like what the gap should be. And we know the invariant 3D Cyber-Witten invariant theory assigns to every 3-manifold. It's actually just a Milnor torsion invariant, some interesting classical topology. So can we construct that from this kind of interesting, like algebraic representation theoretic perspective that Nakajima and then subsequently Braverman, Finkelberg, and Nakajima and other people kind of think about. That I think is like a test case. But also there's like kinds of differential geometry which needs to be done, which I have been thinking about, in part because it's like related to these sorts of problems, like about it's like a gauge version of some things about these Fueter maps, but in some simple cases. So that's all I can say.
Okay, more questions? Last chance. Well, anyway, people have slides which were posted in the chat, so if you have questions, you can probably email to the speaker.
Yeah, I'm happy to chat about this stuff because frankly, not enough, it's too much math for any particular person.
Yeah. Okay, if there are no more questions, so thanks for a very interesting talk. And this is it for today.
All right, thank you.